perché qui non sta mandando quello corretto.
Che dici, possiamo iniziare? Okay, good morning to everyone and those connecting online via streaming. Today we have a seminar led by Dr. Helen Crowley by GME, and she is a leading expert in earthquake engineering and seismic risk assessment. Our colleague Licia Faenza introduced Dr. Helen Crowley and moderated the discussion afterwards. Thank you.
Hi, good morning, everyone. It's a pleasure for me to introduce you, Helen. I met her several years ago in a European conferences, a Seminario project, and I was immediately impressed by her ability to integrate the seismic engineering and seismological community and to understand the essential aspect of both disciplines. Regarding her academic career, Helen graduated in 2002 at the Imperial College London in civil engineering, and then she moved in 2001 to Pavia, where she obtained her master's degree and her PhD in earthquake engineering from the University of Pavia through the European Center for Training Research in Earthquake Engineering. At the EU Center, Helen held a key role from 2006 to 2009, focusing on seismic risk. Her leadership was further demonstrated at the Global Earthquake Model GEM Foundation, where she led the seismic risk activity until 2014, and she served as a Deputy Secretary General from 2012 to 2014. After 7 years of collaboration on various international projects at the EU Center, including EPOS and the first European seismic risk model, which she also coordinates, Helen returned to GEM in 2023 as a Secretary General. Her mission is to lead the Foundation toward Vision 2030, collaborating closely with all other natural communities and sharing new global data sets to move the world toward great resilience against natural hazards. She has received several accolades, including the Plinius Medal Award by the European Geoscience Union in 2009 and the 2024 William Joyner Medal Lecture Award from the Seismological Society of America for her outstanding contribution to the neighboring fields of structural engineering and engineering seismology, and for her ability to work and coordinate large teams involving seismologists and engineering to produce novel and effective risk assessment and mitigation solution. Her research has covered many topics regarding seismic risk mitigation, from the definition of a seismic action for earthquake loss model and seismic design code to the development of regional exposure and vulnerability model for the built environment. Before leading the floor to Helen, I have a technical message for people that are connected remotely. You have the possibility to leave your comment compiling the Google form, which is enclosed with the seminar web link. Thank you. Helen.
Good morning, everyone, and good morning to those of you online as well. Thank you, Licia, so much for that presentation, and thank you also, Licia and Paola, for inviting me to come and be part of this 25th anniversary of INGV. I thought when thinking about what to present, that perhaps it would be interesting to talk about GEM, because for GEM it's our 15th year this year anniversary. I imagine most of you perhaps have heard of GEM. If not, I'm going to tell you a little bit in my presentation about the past, present and future, probably focusing a little bit more on the present and the future. And if you're interested in learning a little bit more about the history, you can read the paper that's been written for the special issue as well. So probably many of you maybe don't know me, so I thought I would just do a quick brief overview of my collaborations with INGV, which have lasted almost 20 years now. I think it's probably 19, but I thought it sounded better to round it up to 20 years. So as I was finishing my PhD back in 2004-2005, I first started collaborating with INGV when the release of MPS-04 seismic hazard model was ongoing, and we were looking at, as engineers, what could be the impact of that release on the seismic assessment of buildings, especially reinforced concrete buildings, and we developed a national seismic risk maps using that model. This is where I heard about GEM for the first time from INGV. They were very supportive of EU Centre potentially hosting the GEM Secretariat, and so they supported us, the colleagues there, in bidding to host the Secretariat. So I was involved in those years. As Licia has mentioned, we then were successful to host GEM, and we created the organisation in 2009. I was also collaborating with INGV scientists after the L'Aquila earthquakes, looking at can you really compare registrations, recordings from an earthquake with a seismic hazard model, a PSHA-04 model, and explaining why it was not right to make that comparison. INGV also led one of the so-called global components of GEM during the first 5 years. We had a number of projects involving global consortia, and INGV led the Global Historical Earthquake Archive. I was also involved in the SHARE project, again involving many colleagues from INGV. Then, as I was looking back through my CV, there seems to be a little bit of a gap. But I think that's because I was quite busy working in Groningen in induced seismicity, and I was not so much involved in research projects in that period. But then the SARA project started, again working with on the European seismic hazard and risk maps, working with Licia on Sheikh Dado was another output. In the RISE project, European Sheikh Map. So many projects with EPOS still ongoing. And now GEM is also involved in addition to EPOS-ON and other projects, the Aristotle project, where we're providing a service for rapid earthquake impact assessment. So I've been very happy to work with many different colleagues from INGV over these 20 years. But as I said, rather than talk about these specific activities, I thought I would focus on GEM in this presentation. So how did GEM come about? I'm not going to talk too much about it, but I think you're probably familiar with GSHAP, the Global Seismic Hazard Map, the first ever global seismic hazard map that was released in the 90s thanks to a collaborative effort of many scientists and natural hazard scientists and seismologists around the world. After that release of that map, there was a gap of a few years, and there was a need, a sort of a feel of a need for not just a map, but a model of seismic hazard around the world, and to go beyond ground shaking and look at the impacts of earthquakes. And so the idea for GEM was that it would be a global earthquake model, not just for seismic hazard, but all the way up to the impacts of earthquakes. And on our website, we have this history, and as I say in the paper, you can read more about the different phases of GEM that there's been. There's been different working programs. There's been different Secretary Generals. I'm now actually the 4th Secretary General of GEM. There's been a number of milestones. We've released OpenQuake, which I'll tell you about. We've released those global components I mentioned before. We've won awards, and we've released the first global seismic hazard and risk maps in 2018. We've then also recently created updated versions of those maps in 2023. So let's focus a little bit more on what or who is GEM today. So we are a non-profit foundation in Pavia, hosted, as I said earlier, at EU Centre. In 2009 was when the non-profit organisation was founded. We were recognised as an NGO by the UN in 2016, and we've always run very much as a public-private partnership, so involving partners from both the public and the private sector and bringing together these two communities. Our mission is to have global partnerships which allow us to become a trusted standard in global earthquake hazard and risk modelling, to lead the community for natural hazards risk assessment, and to be a key resource for disaster risk reduction efforts all around the world. And what you see on the right there is a figure of really what is the GEM Foundation. So it's made up of the GEM Governing Board, which has those public and private partners. It also has a number of non-voting members and associate partners. Then we have the GEM Secretariat, where a lot of the work really is carried out. And there's myself there with the heads of the 3 teams, the hazard team, Marco Pagani, who many of you may know, Vito Silva heads the risk team, and Paul Henshaw, the IT. And so on the next slide, I can show you the people working under each of those teams. So we're around 28, 35 people, depending if you're counting also PhD students, which we do. They're very important to the work that we do, PhD and postdoc students. We have around, I calculated the other day, 70% of the staff have PhDs, so we really are a very scientific organization. We've been talking a lot recently about where are we going. So we're now in 2025. What is our roadmap to 2030? There's a whole document on our website, but our vision is a world that is resilient not just to earthquakes, but to all natural hazards. So how can we support other natural hazards communities? And we want to, whilst earthquake remains really our core business and our core focus, and we want to do the best that we can with earthquake hazards, we want to go beyond ground shaking, looking at liquefaction, landslides, and other earthquake triggered hazards. We want to make sure that we're providing information that's useful for disaster risk reduction, and also strengthening the capacity around the world to assess seismic hazard and risk. And you see at the bottom there a number of different initiatives, and we're planning now activities for the next 5 years that fall within these different initiatives. So how is it that we work? So you've seen that we have this GEM Secretariat, which has a number of people based in Pavia, but it's really very important for us to collaborate with people around the world. And this starts with our governing board, which has representations from a number of organizations in a number of different countries. So on the top left is our public governors. So we have partners in a number of countries, from Italy to Canada to Nepal to Taiwan, Singapore, New Zealand, Australia. We also have associate partners who are the international organizations that you will have heard of, UN, DRR, USGS is another important partner for us. And then on the right, the private sector. So we have a lot of funders and supporters and partners from the insurance and the reinsurance sector. So it's very interesting for us to try and bring together the needs of those 2 communities, the insurance, reinsurance, private sector, but also the public and more humanitarian sector. We collaborate with a number of organizations through projects. We are involved in a number of projects, and those can be funded by European Commission or by the World Bank or USAID. This allows us to really work very closely with lots of organizations around the world. And on this map, we're just sort of showing various countries that we've worked in. We also do a lot of training. So I'll speak a moment about our software, OpenQuake, and that's really where we work a lot as well with different communities, especially early career scientists, to train on the use of this hazard and risk software. In fact, we've done recently a course here in INGV. It wasn't here in Rome, I think it was in Milan, but training on the use of OpenQuake engine. And we hope to do more as well. So focusing a little bit on the different products which are available that you might be interested in accessing and using in your daily research. We have what we call the flagship products. The global seismic hazard map, the global seismic risk map, and the components that are needed to compute those. So a global exposure model, a global model of vulnerability of buildings, and also the OpenQuake engine, which I keep mentioning, which is our software which brings together the hazard, the exposure, and the vulnerability to compute the global risk metrics. Before I go through each of these and tell you a little bit more about each of the components and how they're developed, I thought I would just focus just a moment on GEM's data policy. I know that INGV is an organization that has a very clear data policy as well, and is very good at explaining how results should be accessed through different Creative Commons and open licenses. And we release a lot of our products through open software licenses or open data model licenses using Creative Commons licensing. We also have models which are available for non-commercial public good use, so they're not necessarily immediately openly available, but anyone that requests for them to be used for a public good use case can access them freely, and we will always make them available. And then we also have a number of products which, even though they are openly made available for public good use, if the use case is commercial, we would request a licensing fee. This is just really for sustainability of GEM as well, to make sure that we can then reinvest those commercial funds into the activities of GEM. And our plan is really to reinvest into lower income countries and developing countries and to bring up the capacity of that region of the world. So let me focus first with the OpenQuake engine. This is almost 15 years old now that we've been working on this software. So it's released with an AGPL license, and it can be used for seismic hazard and risk calculations, probabilistic seismic hazard assessment, probabilistic risk assessment, not just through the classical methods that probably you're familiar with and which are used typically for hazard maps and for hazard curves for building codes, but also through what we call a stochastic event-based process, where we are generating stochastic catalogues of events of tens or hundreds of thousands of years. And then for each event, we have the ground motion shaking that could arise from that event, considering ground motion models. We can consider spatial correlation of the ground motions, cross-correlation of the different intensity measures. And we also have just single scenarios which can be modeled, which are useful obviously also for communication purposes or planning. New features that have been added is infrastructure risk, so also to be able to model the risk, not just to single individual assets like buildings, but also looking at pipelines, road networks, network analysis. So these tools have also been built into the software. And we don't just have models for ground shaking, though we do have a lot of models for ground shaking, so ground motion models, but we also now have models for ground failure, so liquefaction and landslide assessment. It's all in Python, it's all open source. We promote standard formats. We try to connect the software to other softwares as well, or at least with our standard formats allow other tools to connect to it. Many different installation packages for Windows, Linux and Mac. And we're really updating at least every 6 months. We're releasing a different version, and then as a stable version every 2 years. And one thing that we do focus a lot on is on performance and optimizing the calculations for very complex calculations, because we do need to be able to run global seismic hazard and risk calculations. So one feature I wanted to highlight about the OpenQuake engine was the fact that it's been adopted by INGV's CPS, Centro di Pericolosidad Sismica, and also the ground motion library is directly used by the ShakeMap version 4 software. And so that ShakeMap version 4 software is used by INGV for the ShakeMaps. So we have over 100, I was trying to count them the other day, but more than 150 ground motion models, I think, that are available. And they are tested. They're tested against data provided by the ground motion modelers. So what this is useful for other people that want to code software that use ground motion models is to make use of those in OpenQuake, because they know that they've been tested against a set of tests. So we use the OpenQuake engine to run seismic hazard at the global scale. And to produce our global seismic hazard maps, we have a mosaic of hazard models. And so this is showing how the globe is split up into a number of models currently. We have over 30 models, some of which are regional and come from regional efforts, such as the ESHM20 effort for the European Seismic Hazard Model. There's national models from the US, from Australia, from New Zealand. There's some models that we have developed together with the community in regional projects, such as in South America. And then some models which were missing, where the team in Pavia, the GEM team, really worked to produce a first model for that region. So all of these models, as I say, are in the same format. So the idea is that we've taken some models, for example, the US model, which uses their own code, Fortran code, but we've transformed it into the OpenQuake format. So all of these models are harmonized in the way that they're described using the standard formats of OpenQuake. With some countries, they've now adopted OpenQuake as their software for running their national seismic hazard models. This is the case, for example, in Canada, in Australia, and New Zealand. And so that is also helping for this harmonization of the way in which seismic hazard is computed in different areas around the world. So this is the global seismic hazard map, one of the global seismic hazard maps. This was released in 2023. So this is just showing PGA, peak ground acceleration, with a 10% probability of exceedance in 50 years. But we have calculated these maps for a number of different spectral acceleration ordinates, not just on reference rock, but also considering the VS30 values coming from the USGS's service, and for a number of different return periods or different probabilities of exceedance. We released the PGA with the 10% in 50 years openly. You can just go and download that layer from our website. The others, you can request for that data to be shared. We've worked with different partners, as I mentioned before, in different countries on their hazard models. This is not one of the models that's in the Mosaic, but it is a model that we've worked with in the Geological Survey in Colombia to help them to develop their national model, and also to support them with a GIS platform to make that model available to the community. So this is just showing the hazard map and how we have a GIS platform for the access to the hazard curves, also to disaggregation data and other outputs of the hazard model. Another feature of hazard modeling I wanted to mention, which is quite interesting, and it's something that I think was really driven by the fact that we have insurance industry partners on our governing board, was this stochastic event set I mentioned earlier. So for most national seismic hazard models, they focus on producing hazard maps and hazard curves and thinking of the needs of the building code, for example. But in the insurance and reinsurance, they really want to relate the hazard to individual events and look at the losses and the impact from those individual events. So this is where we built in those features from the same hazard model that would be used for hazard curves to instead generate stochastic catalogues of events, and for each event calculate the ground shaking. Now, one problem that we have with the mosaic of models that I showed you before is that if you try and generate a stochastic catalogue from each of those models, you're going to get a doubling of the seismicity and overlap at the borders of the seismicity. So what we've been trying to do is to, as a very first step, to identify which region each model is representative. And so then we can put together all of the different models and make sure that there's no overlap, and we can have a single global stochastic catalogue of events. Now, what we hope to do in the future as we go forward is to improve the harmonization of those models at the borders, and to work with the different regions to make sure that we are getting a more harmonized approach to modeling hazard in different regions of the world. But that's more of a long-term effort. In the short term, we want to have a global stochastic catalogue which can come from this current mosaic of models. So this is under development and will be released at the end of this year, at the beginning of next year. So let me leave hazard aside now and move on to exposure. So in order for us to be able to calculate seismic risk at the global scale, we need to model, as a first step, the buildings around the world, industrial, residential and commercial buildings, and people within those buildings. And I don't expect you to read all of the text that's on this slide, but this is just to say that we have a methodology that we apply in each country when we're developing an exposure model for that country. And so we have over 200 countries for which exposure models have been developed. So as I say, the exposure model defines the spatial distribution of buildings, residential, industrial, commercial, the value of those buildings in terms of how much would it cost to replace those buildings, and also how many people can we expect to be inside those buildings during the day, during the night, and during transit times. And we typically use census data. We want to use public sources of data, open sources of data. So the first place we go is to look at the census. And some countries have very good census data. Italy has traditionally been a country that did have very good building census data. Unfortunately, in most countries, Italy, Portugal is another, the census is getting worse and less information is being reported on the buildings. But from the 2011 set, there were quite a few countries, Greece another one, where there's good information on the buildings in the country, at least the buildings in different regions. Some attributes about the buildings, maybe we would know the year of construction, the number of stories, maybe the external material, and all of this can be used to then infer what is the most likely typology of building, which is important for the seismic risk assessment. So for the seismic risk assessment, we want to know, is it a reinforced concrete frame? Is it a frame wall system? Is it unreinforced masonry? This is information that you don't get from the census, but you get from speaking to engineers, from understanding how buildings were constructed in those different countries. So that's also something else that we do, is to collaborate with engineers to understand better the construction practices over time. We also then need to bring in our assessment of how much does it cost to replace the buildings. Are we going to build back better? If there's an earthquake, will it actually cost more to replace the buildings than it actually did to build them originally? And all of this is put together, as I say, to develop a model. It's a model of what is the distribution of buildings and value. This is quite a slow process, waiting for the census to be compiled, going and looking at the data and transforming it into the information that we need. So we're starting now to think about how can we make this process quicker, more dynamic, and updated more rapidly. And I'll talk a little bit about that towards the end of my presentation. So this is showing, apologies that the globe is going the wrong way. I think that might bother some of you. But this is the global exposure model. So the actual exposure models are defined typically administrative regions. So we have the number of buildings in different administrative regions, but then we disaggregate that onto a higher resolution grid, which is what you're seeing here, using proxy data sets. So there are data sets of world population or global human settlement layer from the JRC, for example, which allows us to put the buildings where we know there are people and buildings. So in the version that was released last year, we had just under 8 billion people, 1.52 billion buildings, and there's the area. We also estimate what is the construction area, and also the replacement cost, and everything is put into US dollars. This is another reason why we need to also update regularly the models, because of inflation, because of the changes in exchange rates as well. So that's just to show you the map. So this is in terms of the number of residential, commercial, industrial buildings. We also have maps on the replacement cost, the economic value of the buildings. So that's exposure. Now the next piece that we need to calculate the risk is the vulnerability. So what is the probability of loss to our different buildings in our exposure model? Underground shaking is the first type of vulnerability that we've treated in GEM. So we have over 1,000 building classes that have been defined in those exposure models. And so by building class, again, I mean number of stories, the age of the building, the material, does it have some design code or not, what level of design code. And we also differentiate between whether the building is residential, commercial, or industrial. And so we have collected a lot of information. A lot of people have studied these buildings, have modeled these buildings, have produced numerical models. There's empirical data on the damage to these buildings, and this is all combined to produce what you see at the bottom here with these vulnerability functions. So along the x-axis, we have an intensity measure. This is typically related to the height of the building, the number of stories. So for our low-rise stiff buildings, we're using peak ground acceleration at 0.3 seconds. For our mid to higher rise reinforced concrete flexible frames, we'll be using the 1 second, for example. And then the loss ratio you see there is a ratio of the cost of repair to the cost of replacement of that building, or it could be the ratio of the number of fatalities to the number of occupants. So the way that we develop these models is using an analytical approach. So as I say, we look into the studies that have been undertaken on these building types. What is the stiffness of the different buildings? What is the strength? What is the displacement capacity? And then we create, previously we were modeling all of our buildings just as very simple single degree of freedom models. Now we're moving towards a multi-degree of freedom. We can represent each floor. This allows us to also model peak floor acceleration, and that's important for non-structural elements that are distributed within the building as well. Because we're not just trying to estimate the damage and the losses to the structural elements, but also to the non-structural elements and the people in the buildings. So we're going through a process now of revising our whole set of vulnerability models using this updated approach. So we have simplified numerical models for all of those different building classes. We then run dynamic analysis, so we need recordings. So we're looking to our hazard group, which is putting together a global flat file of recordings from around the world. And so for different regions, we're selecting the records that we should be considering, and we're running dynamic analysis. Based on the response of those models, we see what is the displacement response. We can relate that to damage, and then the damage, we can relate it to loss. And we're not just looking at structural losses and costs, repair costs, but as I said, also non-structural. We also are estimating downtime. So if a building is damaged, how long will it take to repair that building? So we can relate the damage to the number of days that that building's not being used, and that can also be transformed into a cost. We're also producing fatalities and injured people. So the damage, again, collapsed buildings will lead to more fatalities than buildings that don't collapse, and so relating the response again to different metrics of risk. And finally, embodied carbon is something that we're also looking at. So what is the embodied carbon of different building types? It will be a function of the material that that building is constructed with as well. So this is our global seismic risk map. This is one. This is for average annual economic losses in USD. Again, we've disaggregated it onto a grid. So this is combining a stochastic catalogue from the global seismic hazard mosaic of events with each of those exposure models in each country with the vulnerability functions. And this is for economic loss, but we do it for different metrics. We look at the number of buildings. Buildings lost means the number of buildings that are completely damaged for which you cannot repair, or they might be collapsed. Area loss is the equivalent area of those buildings, construction area. Economic loss is how much does it cost to replace the buildings and the contents. Fatalities, loss of life, and also displaced people is another metric that we can relate back to damage. So is the building too damaged for people to go back into? We can very simply estimate that the people in those buildings have been displaced. And so as you can see, if we're ranking here the top 10 countries in the world according to these different metrics, the metric that you're looking at will affect the ranking of the countries. Countries that have specific building types which might have a high risk of causing fatalities due to the heavy roofs or the number of fatalities that they cause when they collapse can be high up in the fatality list. Countries that instead have it's very expensive to replace the buildings would feature high in the economic loss list, for example. We also put this information into what we call seismic risk profiles. So we have on a GitHub repository a number of over 200 different countries and territories where we provide a very simple overview, a one-page overview of the seismic risk in that country, with the values coming from the global seismic risk map, but also including a little bit of information about the buildings that you'll find in that region, as you see in the building classes there. Not just before I was showing you the map of the average annual losses, but we also calculate losses for different return periods. So in a similar way to hazard curves would have different return periods, we can also look at losses at different return periods. So this is something that we provide in these profiles as well. I wanted to spend a few minutes just to talk about the European seismic risk model, just because, as Licia mentioned, this is something that I was involved in, and I was involved in from the other side. So I was not with GEM at the time, but I was in the European community, and in the SERA project was leading the group that was putting together the exposure models, the vulnerability models, and using OpenQuake to run the risk assessment. So we were really looking to GEM to understand what is the approach, what are the methods that they're using to develop exposure models for such a large region, and how are they able to compute seismic risk for such a large area. And the hazard also was using the OpenQuake engine. So we have the hazard model there. We also worked on slightly different methods for site amplification, not just using the slope proxy for VS30, but also bringing in geological era and other proxies. We also worked with GEM very much to use their tools to develop the vulnerability models. So the so-called vulnerability modelers toolkit, which, as I said before, will produce those numerical models and run dynamic analysis. One thing that has transpired from this effort is that the Eurocode 8 has accepted to put the maps from the European Seismic Hazard Model, ESHM20, as informative annexes. So each country can have its own national annex and can have its own hazard definition for. So these two maps are the two maps that you need to define the response spectrum that's used for the design. And each country can have their own, but this is also an informative annex which can be used for those countries which don't have a modern state-of-the-art seismic hazard assessment. Another effort that we did was to work with many engineers in Europe to look at the evolution of seismic design codes. So design codes for designing engineered buildings have changed a lot over the past 60, 70 years. And so we were looking for each country. When was the first time that seismic design was introduced in that country? Typically with a very simple first generation type model where you just had to model you had to ensure that the building had a specific value of lateral strength as a function of the weight of the building. And then the types of codes upgraded from these low codes to moderate codes. They improved over time until we get to the Eurocode 8 style of code. And we were also not just looking at when do we get different codes, but what areas of the country was it necessary to apply those codes, and also what values of that lateral force were imposed. So that's coming really from the seismic zonation maps in the country. So in the bottom right there, you're seeing a video going from 1910 to 2000 of how seismic zonation maps changed and varied over time. With, as you see, Italy popping up as being really the first country where seismic design was introduced. And we use that in our vulnerability models as well, in our exposure models and in our vulnerability models. And this is just the results of the European seismic risk model, just some examples of average annual economic loss and fatalities, and how we combined those two metrics into an index map. Again, we disaggregated it onto a grid, because as you see on the left, the information and the regions at which you present information, it varies country by country. It's better to put things on a grid. So GEM hasn't just worked with Europe, but Canada is another example that have, as I mentioned earlier, I think they're using OpenQuake for their national seismic hazard model, but they also developed their own first national seismic risk model, working very closely with GEM in terms of the methodology and also with the software. We're working now in El Salvador as well. MAN is I think it's the Ministry of Environment. I can't remember the exact acronym, but they are also developing the capacity to have this dashboard which has underneath it all of the models to be able to calculate seismic risk for different scenarios, and also using that in a real time, so as a rapid impact assessment when an earthquake has occurred. Scenarios is something that we work a lot more on than perhaps we did in the early days of GEM. Scenarios are really important to allow us to validate our models. So we've compiled a detailed data set of over 100 events, and they're all available on this GitHub repository. And so each event can be run with OpenQuake. So we have there the information on the rupture, the ground motion models, all of the input files for OpenQuake. And what we're using it for is to run those events and to test our exposure and vulnerability and the losses that we're getting for those events. And I forgot what I was going to say, but it doesn't matter. We need to kind of, we don't go too far back in the past. We like to stick to the last 20 to 30 years, because the further you go back, the less that event in terms of the building is going to be to represent today's losses. Oh, I went a bit too fast there. More projects where we've worked with scenarios. Trek was a project funded by USAID in South America. We worked this is an example in Colombia, to really define what are those scenarios that we should be considering for preparation, prevention, and there was, as you see in the photo on the top left, there was really a sort of a co-development of the scenarios, and then these profiles were developed to show for different scenarios what would be the impact in terms of different metrics that they wanted to see to help them to prepare for possible future events. We've also started to work a lot more in that rapid impact straight after an event space, and this happened particularly after the earthquakes that happened last year in Turkey and Syria, Morocco, Afghanistan. We had just entered into the Aristotle project, which I'm sure you're all very familiar with Alberta and Licia are very much leading, coordinated by INGV. And we were being requested to provide an assessment of what is the impact for these events. And so we've set up now a customized service to be able to run those exposure and vulnerability models. When you have an event that's occurred, it can bring in a shake map from either USGS, but also from a national shake map provider, or you can actually try and model the rupture and specify the characteristics that you want for the scenario and the ground motion models. And so we also have lots of other partners coming that are interested, such as the World Food Programme and other humanitarian organizations that are very keen to have access to what our models are saying, because they typically, we can provide a spatial representation of the impact, so not just global impact, which is important, and which services like USGS Pager provide, but also to get an idea of which are the areas where you might have a higher impact, and also not just in terms of economic loss and fatalities, but going down into the displaced people, the number of collapsed buildings, which can be even more important when you're working in the field and trying to respond to an emergency. So I don't know how long I've got, but I have some more. Okay, some more. These are just a few slides at the end to talk about what are the current scientific questions and issues that we're tackling. In some cases, I'm definitely not the best person to be presenting these. So you'll see at the top right the person that you should be talking to if you want to know more about this. But so Marco Pagani is leading the Seismic Hazards Group, and so they are working on a number of tools for multi-fault rupture modeling. And so they have a software. So inside this link here, you see here to the what's called the Model Builders Toolkit. They have a software called Euler, which is for calculating slip rates for faults, and that's using GNS data and block modeling inversion. These are just words to me. I don't know exactly what they mean, but as I say, Marco can definitely be available to provide you with more information. But then once you get that, it's input into another software, Fermi, which is really for multiple fault rupturing. It does not require you to have already fault segmentation. It relaxes that fault segmentation, and it solves for the sub-fault and multi-fault rupture rates using the slip rates from the faults, but also the regional magnitude frequency distribution. And what the feature really is that it's very quick. The solutions are obtained very rapidly. spatial temporal clustering in hazard models. That's another area of research and where a lot of focus is going, especially with our collaboration with Comet, which is a team in the UK. And we're working very much in the Central Asia region. We're developing time-dependent hazard models using fault sources and a calculator to generate new earthquake sequences that are consistent with principles of elastic rebound and Coulomb stress transfer. We are planning then to test those models with geodetic data. We've seen from that data that there's a bimodality which is not present in our current earthquake recurrence models, coming from strain on large faults, but also distributed strain away from the major structures. So this is sort of areas of research that we're hoping to progress in the next few years for improved time-dependent hazard modeling. Also, ground motion modeling is another area where we're working and using the so-called backbone approach, which has been adopted in the European seismic hazard model. And we worked initially in a project funded by USAID in Central America to produce a backbone approach logic tree. And we're keen to have that backbone approach for different regions around the world. This also goes towards our desire to harmonize the way that we're modeling seismic hazard globally. So in that mosaic of different models I showed you earlier, each model typically will have a set of ground motion prediction equations on a logic tree. Some of those models are very old. The way in which they've been selected is not consistent model to model, and so we're hoping with having these regionalized ground motion models using a backbone approach that's applied globally, we can start to bring some more harmonization into the way that we're calculating hazard globally. Moving on to things that I feel a little bit more comfortable talking about. So Vita, this is also obviously in the field of Marco, but Marco and Vita are looking not just at ground shaking, but at other earthquake-induced hazards, triggered hazards, and the impact from those. So up until now, our global seismic risk maps and models and results that I've showed you only consider the ground shaking. But we need to consider liquefaction and landslides. And so I mentioned earlier that OpenQuake now has a few models for ground failure, and Vita and a PhD student have been developing a new machine learning algorithm for regional liquefaction assessment, probability assessment. So this is the results for Europe, and we will soon have a global map. So it's really just the annual rate of liquefaction occurrence. But let's hope that we can then take that one step forward in terms of the ground deformations and the impact on buildings, at least in a very simplified way, at least to understand which are the areas which would be impacted from liquefaction and where we would expect to have higher damage and loss. Infrastructure risk assessment, our global model is just buildings. We want to also look at globally other types of assets, not just buildings, but lifelines. And so we have a different approach depending on the scale. So we need to also look at how we can tackle this problem at the large scale, at the regional and national scale. And in this case, we also need not just ground shaking, but those other earthquake-induced hazards, liquefaction and landslides, which can have more of an impact on lifelines. And so our first attempts are really just to model the exposure of these elements using open data sets such as OpenStreetMap, which has road networks. And this is a project in Bangladesh where we're really just overlaying the length of roads that are exposed to different levels of hazard, seismic hazard, both ground shaking and liquefaction. But we also have models and methods which can go all the way down to the urban scale, where you do have a lot more information and can really start to model the network. I mentioned earlier briefly environmental impact of earthquakes. So we are assessing in our exposure models the embodied carbon. So the carbon relating to the manufacturing of materials, the construction of buildings, and also the sort of the end of life of buildings, demolishing those buildings. And so when earthquakes occur, we are requiring that there needs to be repair actions in those buildings, and that is generating more equivalent CO2 emissions. And so we can, from our seismic risk model, we can estimate what is the environmental impact in terms of equivalent embodied CO2 And this would hopefully be something that would not just be done for earthquakes, but also for all natural hazards. So our exposure model, which includes this estimate, could potentially be used also to look at how the impact of landslides, of tsunamis, of other hazards on the environment. Machine learning is an area where we're obviously exploring, especially in the risk domain, in the exposure and the vulnerability domain. So I mentioned earlier the very long process that it takes to develop our exposure models when we're going to census data, where we're manually processing that data. We're looking to ways to speed that up and to see if machine learning can help us with that. So one project that Vita has led in a few cities now, but this example here is in Lisbon, is to train the algorithm based on pictures from Google Street View and have engineers really classify those pictures in terms of the numbers of stories based on features, which might be the balconies or specific features, architectural features of that building, which will help you to understand the age. And then to use that as a data set, and then to be able to use Google Street View to very rapidly assess the building types of whole cities. We also want to bring in these open data sets that you might have heard about, these open building data sets. They still have some issues. We find when we compare them with data sets that we have, that often what is identified as a building in those data sets isn't really a building, or at least it's not a building for which we would do a risk assessment. Maybe it's a shed, maybe it's not even a building. And so, but we're seeing improvements in those data sets. So in terms of the numbers of buildings and their spatial distribution, we hope that those open building data sets can be of use. There's obviously other remote sensing data sets, the global human settlement layer from JRC, to get a better idea of where buildings are and how many buildings there are. But then when it comes to the information that's needed for assessing the seismic risk, that's where we need to bring in procedures such as this one I mentioned here. Machine learning is also useful for us for forecasting exposure. We don't want to just look at the risk today, but what might the seismic risk look like in 10, 20, 30 years? Because populations are growing, cities are growing, certain areas of the world, the urban areas are growing very rapidly. And so we have been able to use past remote sense data to train algorithms again, to see what is the increase in the urban density and where are buildings being built, and how has the number of population related to the number of increased buildings. And then we use that to forecast in the future under different so-called shared socioeconomic pathways. There are different pathways into the future, looking at what might the population be under different scenarios, and then we can relate that to how many buildings might we have, where might those buildings be, and also what might the vulnerability of those buildings be, because that can depend on different future scenarios. Will we keep building the way we are today? Will we actually introduce building codes? Will we improve the way that we're building? So different possible futures and assessing the risk under those. So finally, I just wanted to mention our work with other natural hazards communities. So our vision, I think I mentioned it earlier, is a world that's resilient to earthquakes and other natural hazards. That doesn't mean that at GEM we want to do global earthquake, global landslide, global tsunami, global. We want to work with other natural hazards communities that are also already working in that field, but share a lot of our data sources. So we think that the exposure model that we're starting to develop, we can make it more hazard agnostic and make it usable for other multi-hazard risk assessments. But just to mention a last initiative, which is also very strongly supported by INGV, is the Global Tsunami Model Association. So we are working very closely with them. I actually just had a 1-hour meeting with Stefano Lorito about ways in which we can work together. This is an old slide. I'll probably update it following the chat we had earlier. But there's obviously a need to make sure that we're modeling earthquake sources and in the same way between the work that we're doing in GEM and in the Global Tsunami Model. As I mentioned, exposure. Can we make our exposure models more fit for purpose for tsunami risk assessment? Are there some functionalities in the OpenQuake engine that we can add that can support their calculations? And also we want to support them in terms of providing a network, a link to our network around the world, not just in terms of scientists and engineers, but also those industry professionals in that private sector. So with that, I thank you. And if there's any questions, I'll be very happy to answer them. Thank you.
So please, if there are any questions, also from people connected remotely.
Yes. Helen, the question is GEM involved in any site-specific hazard or risk assessment for critical infrastructures?
Yes, so we were involved in a project called METIS. I don't know if you know the METIS project, but it was really looking at the methods needed in hazard assessment for critical infrastructure, especially nuclear power plants. So we have started to add some specific features to the OpenQuake engine for site-specific analysis. So yeah, so the OpenQuake engine, even though we need it to run our global and regional hazard models, we're also making sure all of the features are there for site-specific. We're working, I think it was on one of the slides, but I didn't mention it, non-ergodic ground motion models, working with that community as well that are developing those. I'm sure there's other things I could mention. The OpenQuake engine has been used to validate software that's used for PSHA for nuclear power plants. So it is often used as a benchmark tool as well to check the calculations that have been done for critical infrastructure. So on the hazard side, very much so. On the risk side, again, the software can be used for a risk assessment for not just buildings, but if you have the exposure information, if you have the vulnerability models, it can be used. We've done a few projects here and there, not yet thinking about doing that at the global scale, but hopefully that will come as well.
Other questions?
Thank you, Helen, for the presentation. It's impressive to see all these projects that you have been working on. I have a couple of questions. One is related with how does GEM collaborate with individual governments, local researchers and institutions to create region-specific strategies that align with each country's needs and goals? My second question is on the time-dependent model that you have been shown in the Asia. So I was wondering if there is a reason that you started in that area. My third question is, I don't know if you are familiar with the urban renewal project in Turkey. It's a kind of law. It's called Transformation of Areas Under Disaster Risks. It's forced by 2012 by the government. It's expected to knock down thousands of buildings and renew it. So I was wondering, as an engineer, earthquake engineer, you have been working in that topic. What's your thoughts on that project?
Okay,
Do you think it works or not?
Okay, thank you for your questions. So the first one, how have we worked with governments and local partners? So we have, as I showed, a number of public sponsors. And so we have different organizations on our governing board, some of whom are related to governmental organizations. So in Italy, it's the Civil Protection. And in other it depends on the country. So in some countries, it's more of an organization like INGV or USGS, Geoscience Australia is an example. So in those cases, we're always supporting them, especially on the National Seismic Hazard Assessment and the use of that for building codes. In some projects we've worked in, funded by USAID, we have worked with, especially with city professionals. I think I showed that scenario planning. That's a project called TREC. You can find that on the website, where we were working with specifically with civil protection departments, with firefighters, with emergency managers, to really design together the scenarios and to show how our tools and our data can be used to support that planning. I don't know if I can remember all of the specifics of your question and if I covered them. Oh, the second, yeah, so hopefully that answered your first question. The second question, the time-dependent model, why did we start with Central Asia? I personally don't know. We can ask Marco that. I think we had obviously, through the UK sponsorship, which is from NERC, this idea of having a combined project with COMET, which is based in the University of Oxford and Leeds. It's on BGS, it's a joint initiative funded by NERC, and they were specifically already working, I think, in Central Asia. So I think it was driven more by that project need. But I can take that back and find out more. The last question. We have supported the World Bank with calculations. I think it's related. I must admit, I'm not 100% sure because I wasn't with GEM at the time, but we've supported them with calculations of the impact of the seismic risk in Turkey, and especially now looking in Istanbul more recently for different scenarios and what might be the number of buildings damaged and what could be the replacement cost. And so then there's that cost benefit, as you say. Is it better to demolish the buildings and rebuild them, or try and repair them? I think this is a cost benefit analysis that needs to be undertaken. You have issues, I think, in buildings where you have, if you think of an apartment building with lots of people in the building, that they may have to come to some agreement on a retrofitting technique. There's lots of, sort of more social aspects that need to be considered. But we can at least support with the modeling part of it and the different results you get under different scenarios. Retrofitting, also not just considering the seismic risk, but bringing in energy efficiency can help. I know that they've looked at that a lot in Turkey as well. So more of a holistic view that if I'm going to go into the building anyway to reinforce it, what if I also do some actions which will improve its energy efficiency, and that can help encourage the efforts to reinforce the buildings. But I'm afraid I don't know a lot of aspects about the specific case in Turkey, but again, I can point you to my colleagues who do.
Roberto, a very interesting presentation. Which is the possible interaction between large-scale models like the European and global models and national models?
That's a good question. So we've had that discussion a lot in Europe about is it better to have national models, a mosaic of national models, or to create a regional, and what happens when the regional model is different from the national model? I think from our perspective, it's always very important that we make clear that the models that are released globally and regionally, they are not to be used within a country for design, for construction, that each country has its own national regulations, and to go to those. What we hope by having an open software, an agreed methodology, in having these more regional projects, is to try to bring up, different countries, which are, many of them are often at different stages of developing in their national model, is to try and give them a sort of a benchmark of this is what the community believes collectively is the seismic hazard, and allow them to then compare and contrast and potentially influence the next version of that regional global model. But there will be differences, and those differences come from the need to do a regional model where obviously at the borders you don't want to have a sharp change in hazard. But there's definitely differences, and I think the idea is that with an effort which is regional or global, we can help different countries to access the tools and the methods, and eventually, hopefully, we will have a more harmonized set of national models which match the regional and global in the future.
I do have actually curiosity because I've been impressed by the slide where you show your forecast of the impact. The one in Kathmandu was growing very high.
Yeah.
And you said at a certain point that there was, you said several models, one with the same attitude as today, and one changing also some attitude, which you may tell what they are. And do you know what are the actions that mitigate most the growing on this kind of impact? Because it was impressive. That city was really shocking at certain point.
So,
and also, if you think that as a community and also GEM as a working at global level, there are some action that we can do to changing somehow this trajectory that was really impressive on that side.
Yeah. So actually the slide I showed was just showing the exposure, so just showing the increase in the number of buildings as a function of the increased population in the future. So we didn't, I don't know, maybe it's been done since, I need to speak to my colleagues, but we haven't yet got the impact assessment for those different possible future scenarios. But indeed, you could look at the fact that in some countries, there's not yet a building code. If we bring in a building code, what might the future buildings that are built to that building code, how might that impact the risk? If we start to retrofit our buildings, how might that impact? So yeah, I don't have yet results on that, but I think it's really visually important. It's a very good way of promoting mitigation aspects to show what could happen under different scenarios based on what we can do today. So we're definitely very keen on continuing to work there, but I don't think we have any results yet.
Okay, there are any questions? I think no question from people connected remotely. So we can.
Okay, thanks, Helen, for a very nice presentation. So you just mentioned the fact that the basic point is to have a balance between different countries, different levels of knowledge of evolution for hazard, for risk, and so on. But you also mentioned before that you are doing this kind of real-time estimates of impact of earthquakes, like for Aristotle and for other initiatives. So I was wondering how much the approach that is a global approach, so with many approximations in terms of ground motion, propagation or side effects and so on, how these compare with the real effects for, I don't know, recent earthquakes like the Turkey one of 2023 or the Japan of the 1st January this year, or other earthquakes. If you have made these comparisons to see how much you can really have an information about real time, let's say. Just in time.
That's a very good point. I think I showed a slide with all these scenarios, 100. So that's where we're going, and we're starting to collect more and more information and to run our models whenever there's an earthquake, so that we can start to really understand. As you say, it's very difficult with such national regional models to really get specifics that can be quite local in some cases. In Japan this year, we noticed that the way that we were modeling the timber buildings across Japan, perhaps on average, was fine, but in that specific region, they were worse than we were expecting, or in Taiwan as well, the opposite. So it is difficult, and it's a question that we're kind of posing ourselves now. Will we need to get more into more regional differences, especially on the vulnerability of buildings regionally, where we typically take a more national or regional approach? So we're looking at it more and more. We're testing our models more and more. We would like to also work, or we will work with USGS to put our models through their so the pager system, which is running constantly. And so what happens if our models are just running constantly for any earthquake above magnitude 5, to then see after a few years, we can really start to see where are we overestimating, underestimating. And so this is sort of more of a new field for us. And as we develop our models. So we're putting together a database of scenarios that we can use to validate our models as we develop them. But I think it's typically been the hazard community that's thought a lot about testing, not so much maybe the risk community, but we're moving in that direction.
Okay, no more questions? So we will be your testing case as Aristotle. So we
She
can
has access to the models. You can run as many models as
exactly.
you
I will
want.
test them. Okay, thank you very much to Helen.
Okay.